Good morning friends. Today we will be discussing about a new topic, locus diagram. I will just give you the brief idea before we start about the importance of this locus diagram. Sometimes we are interested in studying the behavior of the current in a circuit when say one of the parameters or one of the elements of the impedance is varied over a wide range. This is applicable in many circuits, especially those who have studied about induction machines. They will know induction motor parameters. In the equivalent circuit you have some variable resistance. So, you can play with this, you can have maximum torque transfer condition, maximum power transfer condition and so on. So, let us see the basic principle involved in this. Suppose we have a very simple circuit consisting of a resistance and an inductance. The impedance is JXL and resistance is R. This is a voltage that is fixed and one of them, either R or XL, is varied. Say R is varied. What will be the locus of the current? Obviously, the total impedance value is changing, the power factor angle is changing. So, the current will be varying. So, what will be the nature of variation of the current? So, if we see the impedance diagram, suppose this is the real part, this is the imaginary part, then it is JXL which is fixed and we are taking different values of R. So, R plus JXL will be say R1 plus JXL, R2 plus JXL. So, the impedance varies along this line, is it not? Its minimum when it becomes purely inductive. So, that time its value is XL, okay. Resistance is 0 and its maximum value it tends to infinity when R is infinity and it will have an angle, you will find this angle will tend to 0. So, at a very large value of resistance it will be practically resistive with an infinite magnitude. Okay. So, this is the locus of Z, all right. Now, what will be the current? Current is V by Z. For the time being, let us forget about the angle part at this moment. So, we can write Y into V, where Y is the admittance. Okay. So, if the locus of Z is known, what will be the locus of Y? Since V is fixed, so the locus of Y will be a scaled version of the current I, is it not? So, how is Y changing with different values of R? Okay. So, for a given supply voltage V, Y represents the locus of Y represents the locus of I in some scale. Y is having the dimension of mho, all right, unit of mho. I is current, ampere. So, obviously, it will be only a scaled version with a different unit, the locus of I with a scale factor V. We can change the scale, that is not a problem. So, our first task is to find the locus of a straight line like this, inverse of a straight line. Let us take any straight line and find its inverse. What is the inverse of this straight line? This is the origin. this is a straight line. I want to know for any point on this straight line what will be the corresponding inverse. So, can you tell me what will be the inverse of this? What will be the inverse of this? Suppose we have O R1, Q1, P1. I have taken 3 arbitrary points. One of them is a perpendicular. All right. I have taken 3 points on this straight line. I would like to see what will be the positions of their inverses, that is R2, P2 and say Q2. What will be the location of R2, P2, Q2 and how are these points changing their positions? Okay. Now, OR1 into OR2 is equal to 1, is it not? Because OR2 is 1 by OR1 and that is equal to OP1 into OP2, it is equal to OQ1 into OQ2, is it not? Is that all right? Now, P1 is a perpendicular, all right. This is a perpendicular, that is, this is the shortest length. Now, from here consider these points P2, R2, Q2. If you remember in geometry you have studied, if I draw 2 lines like this, say O A1 A2 B1 B2. So, O A1 A2 is a line cutting this circle at 2 points A1 A2, similarly this one cutting at B1 B2, then O A1 into O A2 is OB1 into OB2, is that all right? So, if I find OP1 into OP2 is equal to OR2 into OR1 is equal to OQ2 into OQ1, what does it prove? These points A1, A2, B1, B2, C1, C2, these are all lying on a circle. So, Q1, Q2, let us take these 4 points Q1, Q2, P2, P1, these are lying on a circle. Okay. Similarly, these 4 points will also lie on a circle. Is it all right? Now, once again I redraw it for this is a perpendicular, all right. This is 90 degree, OP1 is perpendicular, all right. These 4 points are lying on a circle. So, opposite angles of a quadrangle inside the circle will sum up to 180 degrees. So, if this is 90 degrees, this will also be 90 degree, all right. Similarly, on this side I had taken Q1, Q2, this will also be 90 degree. Okay. So, if this is 90 degree, this is also 90 degree. If this is 90 degree, this is also 90 degree. So, O P2 R2 Q2, O P2 Q2 R2 in this quadrangle, opposite angles are 90 degree. So, these 4 again will form a circle. Is that all right? That means, all the inverse points, that is inverse of the points lying on this, will lie on this circle touching the origin, and OP2 is the diameter, because this is 90 degree. So, the semicircle, this will be a semicircle, similarly this side also it will be a semicircle. So, OP2 will be the diameter. Okay. Therefore, given a straight line, now I know what will be the locus of its inverse. What will be its inverse? Draw a perpendicular, take its inverse and then draw a circle, including with this as the diameter. So, the origin is included, all right. Sorry. So, this will be the circle. Is that all right? So, the inverse of a straight line is a circle. That will include the origin. Conversely, the inverse of a circle where the origin lies on that circle will be a straight line. Okay. So, if I am given a circle, what will be its inverse? How do you determine that straight line? Draw a diameter through the origin, then extend it, take the inverse of the diameter, whatever be that you need, and then drop a perpendicular on this line at this point. So, this will be the straight line which will be the inverse of this circle, all right. So, inverse of a circle is a straight line if the circle touches the origin. Okay. Now, let us take another situation. What will be the inverse of a circle lying outside the origin? That means, the origin lies outside the circle. Will it be again a straight line? So, you join this. Okay. You can take any other line. So, inverse of this, say OP1 is maybe OP2, O similarly, because the tangents are of the same length, O R1 is O R2. Okay. So, these are the inverses. Suppose this is Q1 and Q1 dashed, then Q1 will have its counterpart Q2 and Q2 dashed somewhere here. You will find, we will prove it, they will again form another circle. That is, inverse of a circle, inverse of a circle when the origin is outside the circle is another circle, whereas the inverse of a circle when the origin was on the circle is a straight line. Is that all right? Should I leave it as an exercise or would you like me to prove it? Okay, I will give you the hints. See, OP1 into OP2, okay, OQ1 into OQ1 dashed is equal to OP1 squared or OR1 square, either way, okay, because the tangents are of same length. OP1 squared, this is a constant. Similarly, OQ dashed, OQ1 dashed into Q2, Q2 dashed, OQ2 into OQ2 dashed, what will it be? Equal to OQ2 dashed into OQ2 will be just inverse of these 1 by OQ1 into 1 by OQ1 dashed and 1 by a constant OP1 squared, which is again a constant. Okay. So, what does it prove? The product of these segments is also a constant. Whenever you are having a straight line drawn from a particular point and there are 2 points, the product of these 2 segments is constant, then these points lying on such straight lines will also lie on a circle. Okay. So, all these points will lie on a circle, they are all inverses of these. Okay. So, the inverse of a circle when the origin is outside that circle is also another circle. We will make use of this relationship for the computation of currents, the locus of currents in different situations. Now, so far we have not taken care of the angle part, all right. If we have in electrical engineering, we deal with phasors or impedances with angles. So, when we write V by Z or 1 by Z, the angle associated with Y will be just negative of the angle associated with Z. 1 by Z theta will come out as Y with an angle minus theta. So, whenever we are inverting a circle here, if these represent the phasors or impedances, then this should come in the other segment, other quadrant. So, first quadrant quantities will be reflected in the fourth quadrant. Similarly, if it is R minus Jx kind of impedance function, fourth quadrant quantities will be taken in the first quadrant, all right. So, this is to be taken care of when we handle any problem on circuits. Now, we will also take the scaling factor suitably to get the circles or the other loci of proper sizes. So, we will take a suitable scaling factor and then take care of them while making the final computation. Okay. Suppose you have a resistance and an inductance. The resistance is varied, say between 5 and 50 ohms, okay, and inductance is say given some particular value 4 ohms, J4. We are giving a supply of 100 volts. What will be the location of the current? That is, what will be the locus of the current, and what will be the values of the currents at these two values, say 5 and 50 ohms, or you can take any other intermediate value. What will be their specific magnitudes and angle? So, let us draw first of all the impedance Z. What will be the locus of Z? This is fixed 4j. So, a unit of 4 taken on this side. Mind you, the scales chosen for reactance and resistance should be identical, otherwise a circle might be distorted into an ellipse unless the scales are identical. Both are ohms, so both of them should have the same scale. So, this is 4 and this is varied. 5 ohms on this side will be somewhere here. So, this will be 5 plus J4. Similarly, 50 ohms down the line here, somewhere here say. So, 50 ohms, this has to be chosen to scale. We are not really following any scale here, it has to be drawn on a graph sheet with scale. So, this is a 50. So, this is 5 plus J 4, this is 50 plus J 4. So, this is the location, this is the portion of our interest. Okay. Had it been from 0 to 50, then this would have been the segment, corresponding segment, is it not? So, we are interested in the inverse of this portion. So, we will take the entire straight line. What will be the inverse of this straight line? This is 0, this is 4. So, 1 by 4 is a very small quantity, all right. Now, they are two different entities. This is 4 ohms, 1 by 4 will be more. I can choose any scale, 1 by 4 of admittance can be of much larger magnitude. It all depends on the choice of the unit, okay. They are not same units. So, I can choose a suitable scale for fixing of the magnitude. Say if you take 40 as the scale factor, I have taken a scale factor of say 40, then 40 into 1 by 4 will be 10 units. I can choose the units that way. So, I can choose 10 units here and choose this as 1 by 4, all right. What is the location of the, what will be the circle like corresponding to this straight line? A horizontal line, that means this itself is the perpendicular, all right. So, the circle will be with this as the diameter, you draw the circle. Like this, okay. I will it is getting clumsier, I will draw it once again. As I told you, this is may not be to the scale and a freehand drawing I am making. So, this was 5 plus J 4, okay, O P 1. So, its inverse will be on this line, actually it will be in this quadrant. If we remember that the angle has to be taken care by transferring it on this side, this will be the magnitude, is it not? So, this point let it be P 2. So, O P 2 is 1 by O P 1 in magnitude. Similarly, 5 plus J 50 was here, say here 50 plus J 4. So, its inverse would have been here, all right, wherever this circle is met by this straight line. So, this is the portion which represents that segment 5 to 50 of the resistance plus J 4. Okay. So, this is represented by this segment, inverse of that is represented by this segment. So, you can now multiply for any particular location. So, if I want to calculate for 10 plus J 4, what is the current for 10 plus J 4? Suppose this is 10 plus J 4, this is the point. So, draw a line wherever it intersects, this is the length of the vector which is already magnified 40 times. I have taken a scaling factor of 40. So, that has to be divided by 40, is that all right. So, whatever length you get on this semicircle divided by 40, that gives you, and multiplied by the voltage 100 volts, that gives you the current. So, the current I is, say for example, for P1 OP2 into 100 divided by 40, the scale factor. Once you know that, you can calculate the current also, power also. What will be the corresponding power dissipated? Vi cos theta. Okay. So, this is the real axis. So, cos theta means if you drop a projection, cos theta into, yes, this is our semicircle. Suppose for any position this is the current, then what is I cos theta? This one, is it not? So, measure of this distance multiplied by voltage 100, is it all right? So, V I cos theta will be the horizontal segment of that point on the semicircle multiplied by V 100, of course, that divided by 40 scale factor. What I am measuring as I is actually 40 times I. So, you have to take that into account. Let us take another example. We have a resistance and a capacitance. This capacitance is varied, this resistance is fixed. There is another problem, extension of this. This is J20, this is 10 and this is C. The question is, first of all, show the locus of this current. Next, see this locus is determined. Next, when is the total current having a power factor of 0.4 lagging? For 0.4 lagging power factor, total current, for the total current, what is the value of C? Question is, for what value of C will this total current I have a power factor of 0.4 lagging? Have you understood the question? So, let us try to find out the locus of this first. All right. R is fixed 10 ohms, C is varied. So, XC is varied from 0 to infinity. If it is not specified, then the variation can be over the entire range. So, this will tend to infinity. So, this is the straight line, of which only this is the relevant portion, because x is not varied from plus infinity to minus infinity, it is from 0 to infinity, 0 to minus infinity, all right. So, it is 0 to minus infinity. So, what will be the location of the, what will be the locus of the admittance function? It is 0 to 100 10. So, 1/10 of this 1 by 10. I can choose any scaling factor, all right. Let us choose a scale factor of 200. all right. This voltage is 200, or straight away we can multiply by 200, because after all it is a voltage multiplied by the admittance which gives me the current. So, if I take straight away a scaling factor equal to this voltage, then that represents the current. So, 200 into 1 by 10, that gives me 20. So, 20 amperes, I will choose 20 units will represent with this 20 as the diameter. I will draw a circle. I need not draw a circle, I can draw only a semicircle, because inverse of this will come in the first quadrant. This is in the fourth quadrant. So, inverse will come in the first quadrant. So, this is the, had it been varied over this range also, x is varying with an inductive to capacitive range, then this entire circle would have come into picture. Okay. So, this is the locus of current, I call it I 1, because I will refer to this current here also, I 1. Is that all right? What about this current I 2? It is 100 ohms, 200 volts divided by J 20, it is a fixed current. So, 10 ampere, all right, 200 by J 20, what will be the location? Minus J 10. So, that current is minus J 10. Is that all right? So, this much. This is the location, this is the locus of I 2, this is the locus of I 1. I 1 varies like this with respect to the origin, I 2 is fixed like this. So, what is I 1 plus I 2? I 1 plus I 2, shift this entire thing downward by 10. So, say minus 10, suppose this is I 1, I 1 minus 10 will be somewhere here. So, minus J 10. So, the same semicircle you reproduce here. In this particular example, it so happens this is 10, this is also 10. So, there that means diameter was 20. So, radius was 10 and this side the shift is also 10. So, it so happens that it is touching this foot of the semicircle. It need not be so in all the cases. Okay. Now, what is the question? Question is, for 0.4 power factor lagging, what is the value of the capacitance? For this current, now the current locus is with respect to this origin, this is the current locus, is it not? Total current, the origin is fixed. So, when the current I 1 is 0, the total current is just minus J 10, when there is no current to this is minus J 10 and so on. So, this is the current. For 0.4 power factor lagging, for 0.4 lagging power factor, what is the angle? Cos inverse of 0.4, whatever be that angle. Okay. So, how much is it? Approximately 76, 71, about 75 degrees. Okay. Sin inverse of 0.4 is 4 into 6, to approximately 23, 24 degrees. All right. So, 90 minus 24, it is about say 76 degrees, very crude approximation. So, draw 76 degree here, that is tan inverse cos inverse 0.4. So, this is the current. Is there any other possibility for lagging power factor? Is there any other possibility? Suppose we, okay, let me complete this first. So, this is the total current. So, what is the corresponding current in I1? When the total power factor is 0.4 lagging, what is the current through I1? I know that time what is the total current, this is the total current. So, how much is the current I1? Shift it vertically wherever it hits, this is the current I1, is it all right? Measure of this angle, suppose that angle is alpha. How to get alpha? First of all, you have got the given power factor, corresponding angle you draw here and then find out the current. From there you draw a vertical line, you reach here. So, that gives you the angle alpha of this current, all right. Then how do I get the corresponding impedance? So, draw an angle alpha here, whatever be that, all right, and then stretch it. This is the point x, is it not? If you remember from the current, that is from admittance, if we come back to impedance, the same angle, first quadrant angle will become fourth quadrant and fourth quadrant angle will come to first quadrant. So, z to y or y to z, if you keep on interchanging. So, this was the location of I, that means corresponding to y, corresponding to admittance, this was angle. So, corresponding to z, it will be minus alpha. So, at minus alpha you draw a line that will give you the corresponding reactance, it is 10 plus j x. So, once you get this height, that is 1 by omega c. So, c is, suppose this is p, then OP is 1 by omega c. So, you know the desired c, is that all right. Now, my question, next question was, suppose I give you a power factor of 0.8 or maybe 0.9. So, you draw when the total current is having a power factor of 0.9 lagging. Power factor 0.9 lagging means this much. This is one solution. This also could have been another solution. So long as it is within this semicircle, there can be two possible values, one is here, one is here, all right. Whereas, for the other one, it may not have a feasible value because it is on the other side of the semicircle, which is not there for a capacitive reactance. Okay. So, there could have been two possible. We will first discuss about simple signals, and then at a later stage we shall be using these signals for different analysis, network analysis, representation. Now, signals that we shall be discussing are of two types, one is continuous, the other one is discrete. There are some signals which are by nature continuous, most of the natural signals are continuous. Okay. For example, if you take the record of voltage, if you have a pen recorder, you get continuously recorded values with respect to time, it is recording the value continuously. But there are certain signals which are integrated over time and then they are registered at regular intervals. For example, your energy meter records, okay, or the population that you count after every 10 years. So, these are all integrated signals, by nature they are integrated and hence you take stock, you take the count after certain time. So, they are all, or say sale of tickets, every day's sale if you count. So, after every 24 hours you see how many tickets have been sold. So, most of the records maintained in our offices, most of the records are of discrete nature, they are not continuous. Now, even continuous signals, when you use in computers, you have discretized versions. So, discrete signals are also equally important. Signals, the discrete signals are, say this is a continuous signal, and if we take at regular intervals the values recorded, this will be the discretized version. Okay. So, for example, we measure the power of a particular substation, say at Kharagpur, the substation power we measure at every 1 hour. It is at 12 o'clock, 1 o'clock, 2 o'clock, you record the values. In the logbook they enter these values. So, they are discretized version, not that between 12 to 1 there was no power. Power was there, we assume this to be some average of this. Either the value at 12 o'clock is maintained till the next value is registered, or sometimes for convenience if somebody wants to make any mathematical calculations, any computation, then he can take the average of the two, okay, somewhere in between. So, you join these by straight lines, okay, subsequent the consecutive values you join by straight lines, or you have blocks like this. This is an approximation of the curve that is representing the actual signal. Okay. Now, how fast can we measure these discretized values, or should we measure these values? How quickly should we take the samples? Let us take a sample here and a sample here. Does it represent the signal very correctly? It has gone through a trough. Suppose there is another signal like this. So, I cannot distinguish between this signal and this signal if the signals are taken with intervals so widely separated, all right, samples so widely separated. That means, with large intervals I will be missing out this bottom or the top point. This is, that means, with the signal, if the largest variation that is taking place is represented by some frequency, this represents half that variation. Suppose this can form at the most half of a cycle, half of a sinusoidal function. Okay. This is a maximum possible change, and if I take half that value, then I will be missing out the trough or the peak. So, the sampling frequency should be such that I do not miss out this. So, half the length means twice that frequency that is present. So, maximum frequency that is present, that means maximum number of changes that may occur in the original signal, twice that frequency if I sample the original signal at that frequency, then only I will be able to just recover this point. Okay. There can be some more changes, okay. There can be a peak and trough both, then that means it is varying at a much higher frequency. So, I must reduce the sampling time further to trap that change, otherwise the sampled value will not be representing the original signal. Is that all right? So, this is a very famous theorem, Nyquist or Shannon's theorem. sampling theorem. Okay. That means, the sampling rate should be at least twice the maximum frequency present in the signal. Okay. Right now, we are not going to discuss further details about this. We will be taking up this thing further when we discuss about discrete signals later on. Now, what are the standard signals that we come across? Mathematically, a unit step is a very convenient signal. It can be tested on simple system, simple networks. Suppose you have a battery of some fixed source voltage 10 volts, you are switching it on. If the battery is ideal one, then there is no internal drop. 10 volts supply will appear here after the switching instant, and that remains constant. So, before the switching it was 0. If we count the time from t equal to 0 at the switching instant, then this represents a step function 10 volts. When the magnitude is 1, it is unit step. Okay. This is unit step. Then we have unit ramp. For unit step, we use this notation ut, that is equal to 1 volt when t is greater than equal to 0, equal to 0 otherwise, or in the negative region of time. Okay. This is for the unit step. Unit ramp is a ramp function with unity slope So, f t equal to t into u t. Why into u t? The function t is also having values in the negative region of time, but I want a function which will start from t equal to 0, all right. Before that it is non-existent. So, if I multiply this by a unit step, of this type, then on the left hand side you get 0. So, the usual notation for this will be t into u t. You will find in many books they also write r t. R t means it is a ramp function like this, 0 and then it is like this with a unity slope. If it is having any other slope, then it will be k into r t or k t into u t, okay, where k is the slope. Then we define unit impulse. What do you mean by unit impulse? If you have a step function like this applied for some time tau, if the magnitude is a, okay, this is a pulse of width tau. What is the area of the pulse? A into tau, all right. Now, if we make tau tending to 0, that is the duration of the pulse is very, very small, tending to 0, but the product is finite, a tau is finite, then a must tend to infinity. So, you are having a situation a is very large, not measurable, tau is very small, not measurable, but the product is measurable, that is finite, and when that finite quantity is equal to 1, we call it a unit impulse. Okay. You hit a cricket ball, with a very large amount of force, all right, p is tending to infinity, the duration of contact is very, very small, tau is very small, but p into tau, that is equal to change in momentum, that is finite. So, momentum, change in momentum is this product a into tau, something like a into tau, where you can measure the magnitude of the impulse, all right. So, the magnitude of the impulse can be measured in terms of the product, that is area under this curve, neither by the magnitude of the force A nor by the duration of contact tau. So, this is something like if you switch on a battery and then immediately switch off, you give a kick to a circuit. In a galvanometer, you just apply a voltage and then withdraw. Now, the amount of voltage, say it may be very large, or suppose it is 10 volts, and you apply it for say 1 millisecond, then 10 into 0.1, that will be representing a very small strip, that will be almost equivalent to an impulse of that magnitude. Okay, we will stop here for today, and we will discuss about this in the next class. Next class is now, mind you. Okay. Okay. So, gentlemen, we will continue with the discussions on signals. Last time we were discussing about impulse functions. A unit impulse will be denoting by delta t. This is a function whose value is 1 at t equal to 0 and equal to 0 otherwise, where this function is representing the force. So, this is from 0 minus to 0 plus, or you can write infinity, it really does not matter. That means, the function is coming here, its magnitude is very, very large and duration is very, very small, and then it is going, and this thick line represents something equivalent to this area, all right. So, the integral is finite, when this is 1, it is a unit impulse. Okay. This is time t and this is the function. We normally show it by an arrow and a vertical line. Impulse appears at this moment t equal to 0. So, delta t minus 3 represents what? This is a shifted version shifted version of the same impulse, that is at t equal to 3, this function appears. Okay. Similarly, what will be u t minus 4? It is the shifted version of unit step. Okay. U t minus 4 represents a function which starts after t equal to 4 or at t equal to 4. It is unity after that, before that it is 0. So, any function, if we shift f t is a function like this. Then what is f t minus tau? If I want to represent the same function which is starting after an interval tau, if it is identical, okay, then what will be the mathematical representation of this function? F t minus tau, does it represent this? Cosine b t plus j sine b t. Okay. So, on this side if I separate out the real and imaginary parts, it will be s plus a by s plus a whole squared plus b squared minus j b by s plus a whole square plus b square. Equate the real parts and the imaginary parts, then e to the power minus a t cosine b t will give me s plus a by s plus a whole squared plus b squared. E to the power minus a t sine b t will be b by s plus a whole square plus b square. So, e to the power minus a t into cosine b t is a damped sinusoid starting with a maximum value. This is e to the power minus a t cosine b t. Similarly, e to the power minus a t sine b t. It is like this: you take a pendulum, give it an oscillation, all right, give it a displacement and then let it oscillate. It will oscillate and die down, is it not? And you have a recorder, all right, you just record the image of this point, the bob, then it will be damped sinusoid. If you start your camera when it is in the maximum position, then it will be a cosine function, all right. You move the paper, it will be describing this. If you start from the central position, then it will be this one, okay. So, both are representing basically a damped sinusoid. So, today we will stop here for today, we will continue with this in the next class.